So everyone see that? Nod of the head will do. Okay, well, here's Chop now. Right, I'll let him commit. Morning, Chop.
Morning, Peter.
Okay, we're going to get started now. So, so everyone can see the notes? Good. Okay, so we're talking about cooling towers, fluid coolers, and the considerations for those types of systems. And we're talking about condenser water systems, which we've touched on before on a few occasions. So water-cooled HVAC, refrigeration and other systems transfer heat into a condenser water system, which then transfers the heat into a cooling tower, which is an open system, or a fluid cooler, which is a closed system, or a hybrid cooling tower, which is also a closed system, and we'll talk a bit more about those as we go along. And then the heat is rejected to the atmosphere. Some examples of water-cooled systems that you're likely to encounter at some point in your work. A water-cooled chiller, where heat is transferred from the evaporator to the condenser and then into the condenser water system in the chiller. So here's a water-cooled chiller. Morning, Stephen.
Morning.
In this case, this is the condenser vessel here. The evaporator is up here. The heat from the evaporator is transferred into the condenser, and which is a tube, shell and tube heat exchanger. And then water flows through the tubes of the shell and tube heat exchanger into the condenser water pipes, and then off to the cooling tower or fluid cooler or whatever it may be that's rejecting the heat. I'm going to generally refer to these items as a cooling tower, whether it's a fluid cooler or a hybrid cooler. The general parlance in the industry is to call it a cooling tower, but we'll talk about the differences with those. So there's the water-cooled chiller, might be water-cooled packaged air conditioning units. And I've got a picture of one here, which is a Temperzone unit. This is a packaged unit which has got a compressor and a condenser coil in it. And this can be installed above a ceiling or in an adjacent room, usually fairly close to the occupied space. And it shows a couple of stubs here, which is the condenser water connections. So they're quite useful. If you've got a cooling tower or a distributed system, you can have one cooling tower which serves 100 units if you want to. You just have to pump the condenser water through the building. Water-cooled VRF condensers. So if you've got a VRF system, this is not a very good picture, but these water-cooled condensing units can be located inside the building. You can put them in a cupboard, for instance, or in a plant room, and run condenser water to them. So you don't have a whole stack of air-cooled condensers up on the roof or outside somewhere, and they're more energy efficient. If you're doing a hotel or a similar project, you might have a lot of cool rooms and freezers to reject heat from. Sometimes the mechanical contractors are involved in providing that heat rejection system for the cool rooms. So this is a water-cooled refrigeration condenser. Now, I did a job a long time ago now, but it was a big hotel, and we probably had 100 of these, which were connected to the main condenser water system. So this has got a shell and tube heat exchanger, the compressor sitting on top. The heat, similar to a water-cooled chiller, the heat is rejected from the condenser into the condenser water system and out to the cooling towers. And another one is a water-cooled standby generator. So most large buildings or hospitals, whatever it may be, will have generators. Quite commonly, they're water-cooled, so just like in your car radiator. And usually they may have separate cooling towers, but they might be connected to the main building cooling towers. In any case, they've got to have some form of heat rejection. So they may be connected to the condenser water system, and usually are. So I'll just close all those down. We'll leave that one there. Okay, the typical temperature range of condenser water is between 35 degrees C, leaving the load. So leaving the chiller, it's 35 degrees, and which is entering the cooling tower, and 29.5 degrees entering the load or leaving the cooling tower. That's pretty typical. It comes from the old Fahrenheit scale of 95 to 85, if you're interested, but that's where it came from. So they've kept those temperatures into the SI unit system. In a cooling tower, heat is removed from the condenser water by evaporation of a portion of the water, the portion of the condenser water, due to direct contact with ambient air. So this is why it's an open system. The air and water come in contact with each other. This process often consumes a significant amount of condenser water. In a fluid cooler, it's a dry cooling system and uses indirect contact. So it's a closed system. Indirect contact with ambient air as a cooling medium and does not consume condenser water, but is less energy efficient in heat rejection. So the cooling tower, a fluid cooler, has a tube bundle. The condenser water flows through a tube bundle. Ambient air flows across the tube bundle, similar to an air conditioning unit, if you like. So there's no direct contact of the air and water. It's a dry cooling process. Fluid coolers usually have an integral water spray system, which it's not processed water, to improve the performance of the cooling tower, or the fluid cooler in this case. Okay, so cooling towers are more energy efficient than fluid coolers and are therefore used more commonly. Condenser water systems, which include cooling towers, are open systems, as I said, because water is discharged from the pipework into the cooling tower and comes into contact with the ambient air. This process raises a few issues to be considered and solved, to be aware of. Ambient air is in contact with the condenser water and therefore can be absorbed into the water and is absorbed into the water. Air in the water affects heat transfer and can lead to corrosion. So you're getting oxygen into the air, it becomes corrosive. Ambient dust and particulates are drawn into the cooling tower and then enter the condenser water system. So any dust in the air is taken into the water and can get into your system. This can lead to a buildup of unwanted material or sludge in the pipework and the condensers or heat exchangers. The buildup of this material is normally called fouling. So you've probably heard the term fouling in heat exchangers. So I need to be aware of that. Now, also very importantly, the temperature of the condenser water enables Legionella bacteria to grow. You've probably all heard of Legionnaire's disease, and it commonly comes from cooling towers. So the bacteria will grow in the cooling tower basin because of that ideal temperature for its growth. And then it can be released into the ambient air. So it forms pockets of bacteria in the cooling tower basin. And when the water is disturbed, some of those pockets can be released and blown into the air, and then can be drawn into a building's air conditioning system. And if that happens, Legionnaire's disease can occur. It gets into the air conditioning system, it's carried around, people breathe it in, and it's like a form of pneumonia. And it can be quite fatal. It has been fatal in many cases. So it's important to eradicate that or control it as best we can. The condenser water is chemically treated to prevent corrosion and scaling of the pipework and heat exchange surfaces, and also to eradicate bacteria and keep the water clean for optimal performance. Regular checking of the water quality is mandatory to ensure that Legionella growth is prevented. So that the local councils will require that the maintenance is done on a regular basis and records are kept on site so that they can be checked to make sure everything's being done correctly. It's also our job at times to make sure that that's happening. So if we've got a water treatment company looking after the cooling towers, we may ask them to provide their reports when they do the cleans to ensure that everything's under control. Now, the temperature difference between the cold condenser water leaving the cooling tower and the ambient wet bulb temperature is called the approach. Now, I'm just mentioning these because these are things that are going to be mentioned time and again when you're dealing with cooling towers, and so you need to be familiar with these terms. The approach is a crucial parameter that determines the cooling tower performance and efficiency. The ambient wet bulb temperature, this is another important factor when selecting cooling towers. The ambient wet bulb temperature is a fundamental parameter in the cooling tower selection. As a general rule, as the approach reduces, so the difference between the leaving condenser water and the ambient wet bulb temperature, as that approach reduces, the size and cost of the cooling tower will increase. Higher wet bulb temperatures result in higher approach values and larger cooling tower selections. So if you're in a dry climate, that's good for a cooling tower. So you'll get a nice economical selection. If you're in a tropical climate, say up North Queensland, cooling towers are still used and they work quite well, but they're much bigger because to achieve the approach, you need a much larger cooling tower. I'll just show you a diagram. Just to clarify a few things I'm going to talk about shortly. This is a diagram of a cross-flow cooling tower, and I'll talk about that a bit more shortly. So the ambient air in a cross-flow tower, you've got two sides. Air comes in from two sides. It goes through what's called the fill, which is where the air and water exchange heat. So the water comes back, the hot water comes back from the system at 35 degrees and is discharged into a basin at the top of the fill. So it's just like a trough, a water trough. And it's got a number of little holes in it, nozzles. The water dribbles down through the nozzles. The idea of the trough is to get an even distribution of water over the fill so that you've got an even flow of water down through the fill. Ambient air comes in through the sides and goes through the fill. And then the air comes out in the middle of the cooling tower and is drawn up through the fan at the top and discharged to the atmosphere. And the cold water, 29.5 degrees, dribbles down through the fill into the basin at the bottom and then is taken off by the pumps back into the system again. So again, the approach is the cold water temperature, calling it cold, it's 29.5 degrees, minus the ambient wet bulb temperature. So they're important things to remember. Excuse me. Now, I just mentioned the fill in the cooling tower. The design and configuration of cooling towers, including the type of fill media, commonly called fill, used, the cooling tower size and the air and wet water flow patterns will affect the approach. There's a lot of parameters involved here. There's the approach, there's the water flow, there's the airflow. The motor size comes into it when you're looking at the airflow. So when you're selecting a cooling tower, all these factors need to be considered by if you're doing that selection, you will need to consider them, but usually the suppliers will give you all this information. And these things can be changed. You can change water flows, you can change airflows, and it will affect the performance and the size of the cooling tower. The heat transfer media, called the fill, is a very important component in a cooling tower. Condenser water cascades down through the fill and comes into contact with ambient air to provide evaporative cooling of the water. When the fill is in good condition and clean, it will provide the amount of cooled condenser water that the cooling tower was designed to provide. So when the cooling tower is brand new, everything's nice and clean. It's been designed to achieve the performance that you want, the water flow, the leaving temperature of the water, and so on. But because the air picks up dirt and so on and passes through the fill, it will get dirty over time. It may get damaged when it's being maintained, or parts of it might even be missing. I've seen all these things happen. People take some fill out to clean it or repair it, and it doesn't go back in. So if the fill is damaged, fouled, or missing, the cooling tower will not produce the required condenser water leaving temperature that you've designed it for. Fouling and scaling on the fill media or heat exchange surfaces will reduce heat transfer efficiency and increase the approach. So increasing the approach means the cooling tower is not performing the way you want it to. Regular maintenance and cleaning of the fill and heat exchangers are important to maintain optimal performance. So I've got a couple of pictures of fill so you know what it looks like. These are fill elements ready for shipping out. So it's a PVC or polypropylene material. There are other materials, but they're the most common. And to see it in situ, got a picture of a fellow here cleaning the fill with a high pressure spray. So that needs to be done on a regular basis, because you will get scale forming on the fill. I had a situation on it's a hospital project a few years ago where they were experimenting with, it was a very big project. They were experimenting with reducing the water flows through the cooling towers and to save energy basically on pumping. But we weren't getting satisfactory water flow, water distribution through the fill, and it was flowing too slowly. And there was dirt in the air, as there always is, and we were getting a lot of buildup of scale on the fill. So we had to just had to increase the water flow to a certain level to stop that happening. And having said that, another important thing is to, when you're talking to your cooling tower suppliers, ask them what the minimum water flow is. There is a minimum water flow acceptable for a cooling tower to get good water distribution. There's a lot like we talked about chillers and boilers. There's a minimum water flow. The same applies with a cooling tower. And speaking of fouling, in the condenser tubes of the water-cooled chiller or any other heat exchanger that has condenser water going through it, it's important to have a regular cleaning regime. With the chiller, it's every 12 months. They'll come in, take the ends off the chiller and clean the tubes out, because you'll get this build-up of scale, which affects the performance. I'll close that. Okay, as I've said, sufficient airflow and air distribution within the cooling tower are essential for effective heat transfer. Good air distribution and fan selection help to lower the approach. This normally, obviously, is part of the job of the supplier to you tell them what you want, and they will select the cooling tower, the fan, and the fan performance required. And good distribution of water over the fill media is crucial for maximising contact between the water and the air. Uneven water distribution can lead to localised areas of poor heat transfer and higher approach values. And as I said, scaling. If you get scaling of the cooling tower, it's not going to work very well at all. So these are things that need to be considered when you're designing a system. In order to achieve a lower approach and improve cooling tower performance, it's important to consider these factors during design, installation, and operation. In addition, monitoring, adjusting water and airflow rates, maintaining cleanliness and optimising control systems can also help to minimise the approach. Cooling towers are available in various types. The most common types we use in HVAC systems are cross-flow. So I'll show you a picture of a cross-flow cooling tower. Okay, so it's elevated off the ground there. You've got air coming in on both sides. So you can see one side, the fill covers the full height of the cooling tower. And you've got fill on the other side as well. And in the middle, you can see an access door here. You can get in there in the middle. Sometimes the pipes, the return pipes go up through the middle of the cooling tower in this case. And all the pipes are kept down at low level. I'll talk about that a bit more shortly. In this case, it's an induced draft cooling tower with fans on the top. And this one's got some cowls as well to give the air discharge a direction. And just looking back at this diagram for crossflow again, so you know what a crossflow tower is. You've got air coming in from two sides. You've got fill on both sides. There's a gap in the middle. Quite often there'll be a walkway through the middle here for access to the fill or to these drift eliminators. The drift eliminators are there to reduce the amount of water that's thrown off into the airstream and carried out. We're trying to reduce the amount of water lost in the cooling tower as much as possible. The fan at the top discharging the hot air out. So that's a cross-flow cooling tower. There's also a counterflow cooling tower. I'll show you the diagram first. In this case, air comes in the bottom. The fill takes up the whole body of the cooling tower. So the air comes up from the bottom through the fill. In this case, the water is sprayed over the fill through these sprays. Now, when you're doing your pump pressure calculations, these sprays have a pressure drop, usually around 20 kPa. So be aware of that. If you're doing the pump pressure calcs, don't forget to allow, if you've got a counterflow cooling tower, don't forget to allow for that. And then there's eliminators again as across the top, and the heat is rejected out. So a counterflow tower looks something like this. The black section here is the air inlet. That's a louver section. The fill is in behind the panels here, and the air is just discharged out the top. So that's a counterflow cooling tower. Now you can have induced draft, which is typical. These towers here are induced draft, which means the air is drawn through the cooling tower and discharged out the top. But you can also have forced draft cooling tower. So that's a picture of one. This one's got centrifugal fans at the bottom, which blow air up through the fill. So it's basically the same thing, but the air is being blown through the fill and then out the top. These are relatively expensive and relatively big and relatively noisy. And they're not used very often, but they may have an application. So just be aware that they're available, but sometimes they come in handy. Situation could be if you've got limited height and they want the cooling tower inside a building, sometimes they're going to be a bigger footprint, but they might be a lower height. So it might work in some situation. So, in terms of materials for cooling towers, there's various options, including PVC, galvanized steel, and stainless steel. As the cooling tower is wet and exposed to air all the time, corrosion prevention is critical, so the PVC and stainless steel are the preferred options. Some manufacturers do make galvanized steel cooling towers, but there is a risk that they're going to rust over time. So just be careful in selecting those. They will be cheaper, but they may not be the longest lasting. Okay, fluid coolers. Fluid coolers comprise a tube bundle heat exchanger through which the condenser water flows and exchanges heat with ambient air. I'll just show you a diagram of a fluid cooler. So in this case, it looks a bit like a counterflow cooling tower. It's a very similar principle, but air comes in the bottom through these openings and then passes up through a tube bundle. So you don't have a fill as such. It's actually a tube bundle heat exchanger. So condenser water flows through the tubes and the air passes over the tubes and then discharges out the top. So that's a dry cooling process. There's no direct contact between the water and the air. They're not as energy efficient as cooling towers because the heat rejection is from a water tube bundle to ambient air. So it's a sensible heat transfer going on between condenser water and ambient dry bulb temperature. The wet bulb temperature, as you know, is always less than the dry bulb. So with a cooling tower, you've got a bigger potential, bigger temperature difference, and you've got evaporative cooling working, which gives greater performance. Fluid cooler also contains a water basin and a pump to circulate water externally over the tube bundle to enhance the cooling performance by evaporative cooling of the ambient air. So it's, I'll show you a picture of, well, that diagram shows it anyway. You can see a pump down the bottom. It brings up some of the water, which dribbles down over here, over the tube bundle, and enhances the performance. But essentially, it's a dry cooler. One advantage of a fluid cooler is that condenser water circulates in a closed system and doesn't come in contact with ambient air. This maintains the cleanliness of the condenser water and prevents the water from absorbing oxygen from the ambient air, which in turn prevents corrosion in the pipework. And you don't get the same buildup of sludge and scale because you're not absorbing the dirt from the air into the water. In some cases, these are good if you've got for instance, if you've got a water-cooled packaged air conditioning system, you've got a lot of, as I said before, you might have 100 of these packaged units around the place. It's really critical. They've got very small condensers, and if they get blocked up with dirt, they're very hard to clean. So in that case, you might consider a fluid cooler because that'll keep the water clean. With a water-cooled chiller, they're larger tubes, they're relatively easy to clean, and a cooling tower is more efficient. So horses for courses, you can choose which is more appropriate for the project. A fluid cooler requires much less maintenance than a cooling tower, so that's another advantage. The major disadvantages with fluid coolers are they're generally larger, physically larger than a cooling tower, more expensive and less energy efficient when compared with cooling towers. If you're doing a water-cooled VRF system, I know that some manufacturers won't guarantee the units if you're using cooling towers unless you have like a primary secondary system. So your cooling tower water would have to go through another heat exchanger. And then on the clean side of the heat exchanger, you'll go through your VRF condensers. Some other manufacturers don't mind, they're not worried about it, but it's really to do with build-up of or fouling of the heat exchanger, the condenser in the VRF condenser. So just be aware of that as well, because if you need to have a secondary system, they'll have more pumps, heat exchangers, more controls, and so on. Now, I'll show you a picture of a fluid cooler. So on the outside, that's what they look like. They look like a counterflow cooling tower, but they have a tube bundle instead of a fill inside here. And these nozzles here, or stubs, pipe stubs, are where the condenser water connects to the tube bundle. So I'll just mention hybrid coolers. Hybrid coolers combine dry and evaporative cooling to provide heat rejection and reduce water and energy consumption. They're basically a fluid cooler, but they've got a few more features. Condenser water is circulated in a closed system. There are many different types available from different manufacturers. So as always, if you're looking for a hybrid cooler, look online. You'll find plenty of options. BAC, Evapco, and others, Marley. There's plenty available, but they're all a bit different. One particular type has two finned tube cooling coils. So in the fluid cooler, it's not a fin tube, it's just a tube bundle. So there's no fins. But in the hybrid, this particular type has fin tube cooling coils, so you're getting a greater heat transfer surface area. The first coil operates dry continuously and provides the first stage of cooling. So when the ambient conditions are okay for dry cooling to achieve the required condenser water temperature, the first stage will operate. The second stage coil can operate either dry or wet, depending on the system heat load and ambient conditions. So the first coil will always stay dry. The second coil can be wet by circulating water through it, in the same way as a fluid cooler does. By maximising the running time in dry mode, significant water savings can be realised. When the load cannot be rejected sufficiently in dry mode, in other words, you can't achieve the required leaving condenser water temperature, the second coil is sprayed with water from the integral spray system to boost the unit capacity using evaporative cooling of the ambient air, similar to a standard fluid cooler. If you look at these, they can get quite complex, and they're quite expensive and they're quite large, but they have energy efficiency advantages over a standard fluid cooler. The further enhancement on the system I just described comprises two first-stage dry coils and two second-stage dry or wet coils with two spray pumps and water circuits. So lots of bits and pieces, but greater energy efficiency. And so it provides further capacity staging and water saving opportunities, and potentially greater efficiency than a fluid cooler. Due to the amount of equipment provided, the hybrid coolers are relatively expensive and large, but they have the following advantages. So they have improved energy efficiency compared with the fluid cooler. Again, condenser water is contained in a closed system. It doesn't come in contact with ambient air, and multiple capacity steps are available to save energy and water. Okay, and talk about installation. This is the design of the cooling tower. Well, there's a number of different options available, whether you're looking at cooling towers or fluid coolers or hybrid coolers. We need to make up our mind which type of system we want to use, depending on the rest of the system, whether we're using water-cooled chillers or whatever. And then we can give our requirements to the suppliers, so the likes of BAC, Evapco, and so on, and they will give us some options. They'll make some selections and give us some options. But we have to think about the installation requirements and talk to the suppliers about the installation requirements as well, because it's critical to get it right. Cooling towers and fluid coolers are ideally installed in a location providing unrestricted airflow around the inlet and discharge. This is important to ensure that the required amount of air flows through the cooling tower and to prevent hot, humid discharge air being recirculated into the inlet stream. So looking back at this cross-flow chiller, cross-flow cooling tower, sorry. You can see here, this is on the roof of the building. This is ideal. There's nothing else in the way. There may be some walls around, but as long as the spacing is to the supplier's requirements, that'll work fine. And preferably that the discharge air will be above. If you do have walls around this area, the discharge has got to be above those walls, so the air can get away and get into the ambient airstream and not get recirculated around into the inlet of the tower. What you'll find in practice is building designers, architects often want to hide cooling towers behind walls and even in plant rooms. You'll find this happens quite a lot. These locations need to be looked at very carefully to ensure that the required airflow can be achieved without air recirculation. Consultation with the cooling tower suppliers is really important to determine the clearance requirements. So engage with your suppliers, show them what the building designer wants to do, and you might find that it can't be done. You might say, well, you say to the architect, sorry, we just can't do that. It's got to be on the roof. But obviously, if you can do it, well, they'll be happy with that. The cooling tower leaving condenser water connection is at the base of the sump of the cooling tower and is the lowest point. Accordingly, the cooling tower must be elevated on a frame or piers to enable the connections to be made. It's also necessary to provide suction pressure, flooded suction for the pump to prevent air being sucked through the cooling tower and causing cavitation in the pump. Now, this is quite a common problem. If you haven't got enough, we'll go back to this picture again. If the cooling tower is not high enough above the ground, and if the pumps are sitting on the ground below, it's not uncommon you have to be careful with your pump selections, but you don't want to be sucking air through the cooling tower basin and causing cavitation in the pumps. The pump's not going to work properly. You won't get enough water flow. It's detrimental to the pump because the pump will fail. It'll cause damage to the pump if it's cavitating, and you'll get air in the condenser water system, which you don't want because that causes corrosion and affects the heat transfer. So it's important to get the right elevation for the cooling towers. So it's important to install pipework below the basin level to prevent water losses when the cooling tower is not running. So you've got an open basin and in a cooling tower. So when the system turns off, you've got a head of water in the basin which can leak through the condenser water system. You will have check valves on the pumps, but when there's very low pressure, when the pumps aren't operating, water can leak past the check valves and find its way out. So it's important to keep all the water, all the pipe work below the level of the basin as much as you can. And this also applies to the returning water, the warm condenser water returning to the cooling tower. Keep the return pipe below the basin level until it reaches the cooling tower, and then rise the pipe up to the discharge point at the top of the tower. I'll just show you a diagram of that. So this one here shows, this is the return water, the warm water coming back. You can see that they're running the pipe below the water basin level of the cooling tower. And then it rises up to the top of the tower. Now, obviously that water, there'll be a head of water above the basin when the cooling tower turns off. And if there is a risk that some of that water will be lost. You can use motorized valves to shut off when the system shuts down, and that'll hold the water back. Check valves will to a certain extent, but they can leak. So that's really important to keep the main runs of pipe work down below the basin level of the cooling tower. And you can see it in this one as well. This pipe here is actually I believe it's a bit hard to see, but I think that pipe goes up through the middle of the cooling tower to discharge water into the basins at the top. And this pipe, the lower pipe, will be from the basin. So that's the cold water down here, and this is the hot water coming back. So these things are just important to be aware of and make sure you implement them when doing your design. It's also preferable to install all the isolation and balancing valves at low level for easy access, so you don't have to climb up to the top of the cooling tower to fiddle around with valves to try and get the balance right. And try to arrange the pipework in a symmetrical layout to assist with balancing the water flows. You want to get the same flows going through each tower when it's operating to get good distribution. So once again, looking at this diagram, you can see these valves are at a low level, so a person can stand there and adjust the valves. It's better being down there than up the top where it's difficult to get up there to get to them. Now, there are code requirements for cooling tower discharges, so ensure that you've complied with that, and obviously to prevent contamination of outside air intakes. When choosing pipe materials, consider the potential corrosion in open systems. So for a closed system, if you're using a fluid cooler, you haven't really got any concerns with corrosion in the pipework. So you can use steel pipe, for instance, if it's a large system. Normally you'd use copper pipe up to a certain size, and then you'll go to steel if it's, say, above 150 millimeters. But with a cooling tower, because you've got potential corrosion, once again, you'd use copper up to 150, and then you might use stainless steel above that. But steel is at risk of corrosion if you use that in an open system. Sometimes people use spiral welded stainless steel, which is a cheap form of stainless steel. It is less expensive, but it's you've got to be very careful on the suction side to avoid implosion of the pipe. If the system's looked after properly, this won't happen. But I have experienced it more than once, where someone's come to maintain a cooling tower and they've closed the suction valves without going to turn the pumps off. So you've got to, in designing it, you've got to try and prevent this happening. If they close the suction valves on the cooling tower and the pump is still running, you're going to create a high suction pressure in that pipe. And I'll show you a picture of, this is actually not a condenser water system, but this is what will happen. If you're using spirally welded stainless steel for condenser water, and someone does that, leaves the pump running and shuts the valves, it'll just go boom and collapse. And I've seen it several times, to be honest. And so that also comes down to selection of materials. So if you want to use spiral welded stainless steel to save money, be very careful that doesn't happen. Something to be aware of. You can get seamless stainless steel, and you won't have any problems with that, but it's obviously a lot more expensive. In some cases, the fan discharge is ducted. This may be required if a discharge sound attenuator is required, or if the cooling tower is installed in a plant room, or if the cooling tower is surrounded by walls higher than the cooling tower. So as I said before, you want to get that discharge up above any walls. So you have to ensure that the additional static pressure is allowed for in the cooling tower fan selection. So in other words, you need to tell the cooling tower supplier that you've got additional static required on the discharge, and they'll select the fan accordingly. If you don't allow for that extra static pressure, the fan selection won't be good enough, won't have enough pressure, and then that will affect the performance of the cooling tower because you haven't got enough air flowing through it. So all these things are important. Now, you also need to eliminate dead legs. Now, I'll tell you what they are in a second. Or stagnant parts in the pipework. In other words, ensure that condenser water is flowing through all parts of the pipework during normal operation. You want to get the chemicals flowing through the whole system. You don't want parts that dead leg means there's no water flowing through there. This ensures that the water treatment chemicals are reaching all parts of the pipework and thereby preventing the potential creation of bacteria growth. So you can get this Legionella growing in dead legs if there's no water flowing through there. Temperature range of condenser water, as I said, 29.5 to 35 degrees is ideal for the growth of Legionella. So we need to take all measures to prevent it. Some people ask, how do you define a dead leg? So here's a definition here that's probably useful to you. It's any bit of pipe that branches off another main pipe and has a length longer than the internal diameter of the main pipe. So if you've got a branch coming off, so it's 150, you've got a branch coming off which is 50. If it's longer than 150 long, it'll be considered a dead leg. So you need to design the piping system so that you've got water flowing through the whole piping system when it's running. Other components of a cooling tower system, such as offline chillers or standby pumps, may also become dead legs. So be aware of that as well. When we have multiple cooling towers in a common system, so they're all connected up to the same common pipework, it's necessary to provide a balanced pipe, or sometimes called an equaliser line. This goes between the sumps to ensure that the basin water levels are the same for all the cooling towers. If the basin levels vary, there's a risk of running a basin water level too low and sucking air into the pipework, with potential risk of corrosion and cavitation of pumps. So the equaliser line is there to ensure that those basin levels stay the same. It also depends on the balancing of the water returning to the cooling towers. So it's when you're commissioning cooling towers, you've got to get all those things right. Get the water flow to each tower even, and then you shouldn't have too many troubles. Side stream filtration systems are often installed to continuously remove dirt from the cold water basin of a cooling tower. Side stream filtration system comprises pipework and water nozzles in the water basin, which are connected to an external filter and pump. So I'll show you, there's information available online, but I've got a typical system here. This is from Masterflow, so you can have a look at their website. This is the filter. It's a filter with a pump. And this is a diagram of the cooling tower basin. So you put pipework, PVC pipework in the basin of the cooling tower and adductor nozzles, so spaced around the basin of the tower, and they blow water. So it's recirculating the condenser water in the basin, and it pushes the water out through the adductor nozzles in the basin and stirs up the dirt in the basin, which is then drawn back through the filter and recirculated. So it's trying to reduce the amount of dirt that's building up inside the cooling tower. So you'll find on most jobs, there's another picture here that sort of gives you an idea of these, if you can see those parts around the basin, they're the adductor nozzles, which send a jet of water into the basin and stir up the dirt, which is then returned to the filter. This is pretty common now in all cooling tower basins. You'll find that they're going in. Okay, now there are statutory requirements for cooling tower maintenance. As I mentioned before, the local councils will be, a cooling tower has to be registered, so the council knows it's there and it's got to be looked after. The idea being principally to control Legionella, because nobody wants Legionnaire's disease to occur in their local area. So part of the requirements are that the cooling towers must be drained and thoroughly cleaned on a regular basis. If there's only one cooling tower, this means that the cooling plant will be unavailable during the maintenance activities. Typically, this is not acceptable, and therefore you need some redundancy. And that's so we usually need more than one cooling tower. You'll usually have two cooling towers so that one can be clean and the other one is still running. Depending on the height of the cooling tower, access ladders and or platforms will likely be required. So this is another important thing to consider, access to all the parts of the cooling tower or fluid cooler. Typically, the fans are located at the top of a cooling tower, so a ladder, at least a ladder, will be required and a platform so that you can get to the fan and the motor up the top. I'm going to talk a bit more about access in a moment. I'll just mention one other thing. Often variable speed drives are used, and nearly always now, you'll have a variable speed drive for the fan motors to control the capacity of the cooling tower. So if by reducing or increasing the airflow through the cooling tower, you're going to change the capacity of the cooling tower, which is going to change the leaving water temperature. So there's a temperature sensor in the common cold water leaving the cooling tower. That sends a signal through the control system to vary the fan speed to control the leaving water temperature. That's a standard control method to control that condenser water leaving the cooling tower. And you get energy efficiency, energy savings. You can reduce the airflow at times when the ambient conditions are suitable to save fan energy and still maintain the condenser water temperature that you want. So access is required to at least these components: fans and motors for a cooling tower and fluid cooler, warm water discharge basins and spray nozzles, drift eliminators, the heat transfer fill for cleaning, repair or replacement, heat exchange tube bundles, in a fluid cooler, cold water basins for cleaning, adjustment of water makeup, repair of leaks. Water makeup is another thing that you need with a cooling tower because, and with a fluid cooler, because of the evaporation that's going on. So you've got to keep the water levels up. You need access for repair of leaks, inspection or repair of side stream filtration systems. In a cooling tower, you need to inspect pipework and repair leaks, cooling tower. You need access to the side stream filter and pump. So in order to gain access to these components, there may be a requirement, and usually is, for safe working platforms in accordance with relevant legislation. So safe working codes will spell out what access you need, safe access. Different regulations may apply in different locations, but in general, access platforms will be required where work can't be carried out safely from the ground. Okay, so some of the drawings, some of the pictures we've already seen. This one, you can see there's an access ladder up the side. There's a platform on the top, so you can get to the water distribution basins. You can get to the fans. Also, for a cross-flow cooling tower with this access door, there's usually a ladder inside, so you can climb up inside. You can clean the fill. You can take the fill out. I'll show you another picture. Here's one with multiple levels. So the bigger the cooling tower gets, the more levels you're going to need for access. So this one's got a lower level, which will get you access to the fill at the lower level, the water basin. Then you may need to get, or you need to get up to the top as well. So you've got access to the water distribution basins and the fans. Maybe a little bit hard to see, but I'll see if I can make that a bit bigger. You can see at the top here, you can just see these pipes coming out. So this is a cross-flow cooling tower. The fill takes up the entire side on both sides. The pipes, the return water pipes, the hot water pipes are coming up through the middle of the cooling tower and then distributing out to each what's called a cell of the cooling tower or to the fill. So there's a water distribution basin at the top of each of these cells. So you can see those pipes coming across to the water distribution. Yeah, so you need access to all those things. The water distribution basin may clog up with dirt. So you need to clean them out periodically as well. So there's a fair bit to absorb there, but I just wanted to give you some awareness of what's involved and things to think about when you're selecting cooling towers. So cooling towers and to a lesser extent fluid coolers have many design, installation and operational aspects to be considered. Cooling towers are more energy efficient than fluid coolers, but have a lot more maintenance requirements and are strictly regulated because of potential Legionella growth. The choice between a cooling tower and fluid cooler will depend on the project size, equipment costs, physical dimensions, energy efficiency requirements, maintenance requirements, environmental considerations, return on investment, to name a few. Quite a few things to think about. As always, there is a wealth of information available online and from suppliers. Engaging with suppliers early in the process is important to optimise selections and obtain detailed information on the installation requirements. Can be a bit of a job to work through offers for cooling towers. When you're asking suppliers to give you a quote for a cooling tower, you'll ask, say, for 3 or 4 different quotations. They'll all have different selections, different requirements, different access requirements. They'll also offer you multiple options. So it can be quite a job to work through it, but understanding the fundamental requirements is it's important so that you can make the best selection. So we're right on time. Any questions?
Hey, Peter, I got a question.
Yep.
It's about the point where you should ensure that you eliminate dead legs or stagnant parts in the pipework, and to consider the case when there are any chillers or standby pumps that might not be operating, maybe in winter when the heat capacities, that the cooling capacity is not required. So in that case, would you just rotate the operation of your multiple chillers and just kind of take turns to operate? Is that a sufficient measure to take?
Yes, that's one option for sure. Yep. You can, and normally you do that anyway with chillers. You have them running, they might run for a day or 2 days and then swap over to another one. If you're in part load situations, you want to keep the water circulating as much as you can. Yep.
Is there
definitely.
any like typical frequency in terms of how often you should rotate it?
Different clients, different owners of the building will have different preferences, but you know, if your chiller's running fairly constantly, you might change them over once every couple of days, perhaps once a week. So, you know, as long as, I mean, it's the Legionella is going to take some time to grow, so it's not going to happen instantly. So as long as you're maintaining some flow through all those components on a regular basis, you should be okay. And if the chemical treatment is done correctly, which it has to be, then you're killing off any bacteria anyway. But I suppose dead legs are more common. Trying to think of an example where it's more common in a small piece of pipe that sometimes doesn't get much flow. Yeah. You know, I mean, it may not happen, but and say the equalizer pipe between cooling towers, and you want to maintain a flow through there. That's a fairly common point of risk is the equaliser line. So commonly because that's quite a large pipe, it has to be, because there's not much pressure there. It's only the pressure of the cooling tower sumps and the difference in height of the water is creating the pressure to allow water to flow through the equalising line. If you can imagine that. There's not a pump pushing the water through, it's just the head of the water in the basin. So the flow through the equaliser line is very slow. And if the levels are all equal and maintained level, there'll be no flow through the equaliser line. So the equaliser line is an ideal spot for Legionella to grow if you have that situation. So what's commonly done is the flow to the side stream filter system is taken from the equalising line. Instead of taking it out of the basin of the cooling tower, you take it out of the equaliser so that you've always got flow through the equaliser, and it goes down through the side stream filtration and back to the sumps. Excuse me. That's something that I haven't mentioned in the notes, but that's something to keep in mind as well. But that's the ideal place to get the suction line for the side stream filtration out of the equaliser. So that's probably your biggest risk. And if you can keep the flow through there by using a side stream filtration system, that's going to eliminate your main risk of dead leg. But there could be other situations. Just be aware of it. That's all.
Thanks.
Any others? No. Okay. All right. Well, thanks for your attendance. I hope it's been of some use, or will be in the future. May not be right now, but you've always got the